look at the control of some enzyme catalyzed reactions. So we're going to visit this again where we looked at the Michaelis-Menten enzyme, where you're forming the enzyme substrate complex. So the first step, where you have an enzyme, you have a substrate, they come together, you form the enzyme substrate complex, the ES. And that's best described by Km, which is the strength of the attraction between these two things. How strongly is that substrate bound to that enzyme? And then the next part, step two, is like when the reaction happens. And we describe that by the Vmax, which is the reaction rate. How quickly does that reaction happen? And that can be affected by the concentration. So the more substrate you have there, the easier it is for the enzyme to find that substrate, to bind it, and then the reaction should happen faster. You should get an unchanged enzyme and then a new product. So how do we inhibit that? Inhibitors are any compounds that are going to reduce the enzyme's activity in any way. And we can either we can attack this with a competitive inhibitor where the substrate and the inhibitor look the same, or it could be non-competitive, combined somewhere else. They can bind reversibly or irreversible. So irreversible inhibitors are ones that are going to bind the enzyme and produce a non-functioning catalyst. So basically, they deactivate that enzyme permanently. This is what happens with aspirin. So aspirin is going to bind to this cox, or sorry, yes, aspirin acts as an irreversible inhibitor. It binds to the COX enzyme. It transfers an acetyl group, and then it's deactivated. And then the COX enzymes, these are the things that catalyze the production of prostaglandins. So you might remember when we studied prostaglandins in the lipid chapter. They're responsible for pain, fever, inflammation. And so if you can inactivate this enzyme, then you're not going to have those things. So it's going to reduce the inflammation. So the irreversible inhibition by aspirin will block those symptoms. So that's a irreversible inhibitor. You can also have reversible inhibitors, and they're going to bind and then just interfere with that activity, but the binding is not going to be permanent, and the inhibitory effect is just going to be temporary. So reversible, it's going to bind, and then it will not bind anymore, and then your enzyme is going to be fine. So the enzyme is unharmed in that case, but it also only has a temporary effect on whatever reaction you're trying to inhibit. Then you have competitive inhibitors and then non-competitive inhibitors. Competitive inhibitors that's when the inhibitor is going to look a lot like the substrate. They're going to have a lot of structural similarities because they're going to bind to the same active site. This is really going to affect that first step where you're forming, the enzyme substrate complex. So instead of your substrate here, your inhibitor is going to form there. So it's going to affect the Km and not so much the Vmax. And these are just a few different examples of competitive inhibitors. So this drug right here is converted to this one, and it's going to be the competitive inhibitor of this guy. So this is the real substrate, and then this is the inhibitor. So you see they're like almost identical. The difference really is in this nitrogen is in a different place. So just you're switching nitrogen here to here instead. So the shape of it looks very, very similar. And so instead of binding your substrate, it binds this molecule, and then that enzyme doesn't work anymore. This is also a drug over here, the sulfonamide, and this is the drug, and then this is the substrate that it is inhibiting. So again, you can see a lot of structural similarities there. Then you have non-competitive inhibitors where it's going to bind to a different site on the enzyme other than where the substrate binds, and that binding is going to cause a change. It's going to slow it down, or it's going to interfere with the Vmax, not so much the Km, but the process by which the reaction happens. So that's the Vmax. So I love this diagram. I like this, how the book kind of explains this. And so in part A over here, this is your normal process. You have your enzyme, you bind the substrate, you form the enzyme substrate complex, and then you end up with your enzyme in your product. So this process that they're describing is really just a guy peeling an orange. So if you peel, you have to pick up the orange, and then you peel it, and then you end up with the guy and a peeled orange. Now, what happens when you throw in an inhibitor, different types of inhibitors? So this first one is going to be a competitive inhibitor. And so they say instead of having just a box of oranges, you might have some orange balls in there as well. And so sometimes when you put your hand in the box, you pick up an orange, and sometimes you pick up an orange ball. So if you pick up the orange ball, no reaction happens, right? That's going to inhibit the reaction process. This is going to be a reversible inhibitor because you can just drop the ball back in the box or somewhere else, and then maybe you'll pick up an orange and you're good to go. That's a competitive inhibitor because those oranges look a lot like the orange balls, and that's going to affect, how well um, the enzyme substrate complex forms. Over here, this is a non-competitive inhibitor, and suppose when the guy's peeling the orange, instead he puts on a glove, on the other hand, an oven mitt. When the oven mitt is there, he can still bind the orange, but then he can't really peel the orange when he has that glove on, so that inhibits the process by which he's able to peel the orange. Not how well he's able to bind the orange. He can still pick up the oranges in his right hand, but he can't peel them anymore. And so that's when that enzyme, the process breaks down, and that's inhibiting the Vmax there. So you have your competitive inhibitors, non-competitive inhibitors. The competitive are going to bind at the same site. The non-competitive ones will not bind at the same site. So which statement accurately describes a competitive inhibitor? So a competitive, that's going to bind at the same site as the substrate, so right at the active site. So it's going to change the Km for the enzyme, right? So this is what's going to happen here. It's going to, oops, yeah. All right, so it's going to change the Km for the enzymes. Whereas a non-competitive inhibitor, it's still going to be able to bind the substrate, right, with this oven mitt, but he can't peel it as fast. So it's going to affect that second step of the reaction. So it's going to change the Vmax of that reaction. The book goes through kind of an interesting discussion on Tamiflu and how Tamiflu and Relenza work as anti-flu drugs. And so here's a flu virus, and you've got these different enzymes. This is an RNA virus, and this is the shell. And then on the surface, you have these different enzymes, and we'll call one N and one H. And if you remember the H1N1 virus from 2009, that would make sense. So you have these different types of enzymes, and they do different things, which is why they're called H and N. There's 16 types of these of H and 9 types of the N enzymes on a flu virus. So that's so when they're so flu viruses are classified by what particular H and N enzymes are present. So the H1N1 strain of 2009, these were pretty bad flu epidemics. The H5N1, that was a bird flu. So how do these drugs work? Or actually, let's look at the how does the flu virus work? So here's a picture over here. So you have your virus. It attaches with this enzyme, this H enzyme, to the surface of a cell, and then it's engulfed inside that cell and starts taking over the cell's machinery. It makes its own, RNA. It replicates itself. And then it buds off, attaches to the surface, and then the N enzyme comes in, like breaks this bond here, and then it releases it into the body, and then each one of these will go and affect another cell, and so on and so forth. But the anti-flu drugs like Tamiflu and Relenza, what they do, they're competitive inhibitors, and they block the ability of that N enzyme to break this off. So the N enzymes aren't going to work. They're not going to release this. So it doesn't affect this part. The cells are still going to have the flu virus in there. They're going to make them, but then they can't be released. They're not going to be released into the rest of the body. So they're not effective against all flu viruses, and some of these can undergo, genetic mutations, and then the drugs won't work anymore.